able to join us. There we go. So I wanted to start off with an announcement that your instructor is a moron. In case you hadn't figured this out, like what? No, really. I added a whole week to our semester in my syllabus. I swear, every time I plan a syllabus, the first place I go is the academic calendar so I can get all the breaks and things in there. And I made a note in my calendar that the end of the semester was the 14th. And in my head, that meant end of classes. And so the next week was finals. And then someone emailed me from the other class and is like, yeah, no, the semester is over on the 14th. So this morning, um, with Sneaky Sasquatch playing in the background, which is my son's new favorite video game, updated our syllabus to actually end when the semester ends. So most of the stuff in terms of the due dates is the same. It starts April 5th. I had to push basically all the due dates from that point forward up a week. But everything up to that point is pretty much the same. So just wanted to give you the heads up for that, that our classes will end on time. The week of finals week, we will not meet, except that I will hold office hours during the times that I would normally be teaching, just in case there's any last minute homework questions or anyone needs to catch up. And that way we can all finish on time on the 14th. So how's that sound? Better? Yes, better for some of you, especially who are planning the rest of your lives, but it's always good to stay on schedule, or for the most part. Let me see here. So I fixed that. I updated the downloadable version of the syllabus in case you're one of those folks who likes to have a paper copy. That copy is currently up to date as well. Alrighty, there's a nice pretty picture for us. Another beach scene. That's my preferred wallpaper background for my computer. Tell me what you remember from last time.
Okay. If the mean is lower than the median, it's a negative distribution. Is that? And if it's
Negatively, need another noun in there.
negatively directed, I negatively facing, the tail is to the left,
Looking for
and
a
then the
word that
tail
starts
is
with an S.
Skewed, negatively
skewed,
skewed.
Yes.
skewness. And if the mean is higher than the median, then skewed to the right, so positively or positively skewed.
Yes, that is true because the mean is being pulled by the tail. So the median is sort of the middle of the data. By definition, half of the cases are above the median and half are below. It's the 50th percentile, but the mean doesn't have that property. The mean can get pulled by the larger values. So, sorry, I'm doing it backwards. Pulled positively or pulled negatively. Yes, good. What else? Oh, new beach scene for you. New vocabulary besides skewness. So we had standard deviation and its cousin, standard
Error.
error. And deviation and error sound like synonyms. Are they the same thing or are they not the same thing? They're not the same thing. Do you remember the difference?
I just peeked at my notes, but standard error is not about individuals, it's about the mean.
The sample, yeah. Yes, and it's okay to peek at your notes, by the way. This is not like a quiz show. I expect you to phone a friend or, take a lifeline, whatever your favorite game show tendency is nowadays. That show's not on anymore, right? How to become a millionaire? Or somewhere on the game show network, maybe. I'm not privy. I did know that they brought back Name That Tune, which I am a fan of. And then they had Fox had a version that was Beat Shazam a couple years ago that I was a big fan of because then you could play at home with the app. So you could actually beat the contestants, which was wonderful. But this is not a game show, it's just a review. So you're allowed to use your notes. So, yeah, the idea is dispersion versus inconsistency. So, mean and standard deviation are ways of characterizing one sample of individuals. The mean is an indicator of central tendency, although it can get pulled by the tail, as we just discussed. Standard deviation is defined as how far off on average each individual's case is from the mean. So standard deviation is this idea of dispersion, spread. It's if you take it and square it, then that gives you what? Standard deviation squared has a special name.
Variance.
Variance, very good, yeah. So then if we're talking about one sample of people, they have a mean, they have a standard deviation. Standard error then is thinking about a sample of samples, not a sample of people. So the definition of standard error of the mean that we started talking about last time and we'll return to is the average distance of a sample mean from the population mean. So you can think of it as how noisy the estimate of the sample mean is expected to be across samples. So if I grab a sample of 10 people and I compute their mean, and I grab another sample of 10 people and I compute their mean, how far off can I expect those to be? That's the idea of standard error, where it's offness relative to the population mean, which we never know unless you play God and make fake people, which is what I also do for a living, otherwise known as simulation research and quantitative methods. Do you remember the two things that contribute to standard error? What things result in more inconsistency across samples and what the mean's going to be? No guesses? Is that where we should pick up with then? Would that be good? Maybe? Fair enough. Let me pull up that slide because that's where I knew we were going to end up. Clairvoyance. All right, so I am on, let's go with slide 33 to demonstrate what I'm talking about. So these pictures that we're looking at here, these are histograms that characterize the distribution of what the sample mean would be across 1,000 repeated samples of the same size, drawn from a distribution with the same variance. So the upper left-hand corner here on slide 33 is if I were to take a sample of 5 people, another sample of 5 people, and I drew them from a population where the standard deviation is supposed to be 3. So on average, any one person is off from the mean by 3. This distribution characterizes what variability we would have across repeated samples of the same kind in what the sample mean could be. Now it gets it right, sort of on average. The gray line here shows what it's supposed to be in the population, which I know in this case because I made up the data. It's centered around 10 like it's supposed to be. But what the mean could be in any one sample is anywhere from like 6 to, let's go with 15-ish. So there's a lot of noise, a lot of inconsistency. Another way of thinking about that is, what is the variance of this distribution right here? Standard error is analogous to the standard deviation of the sampling distribution of the mean. So the average offness of the sample mean from the population mean is the standard error. If I contrast this picture up here in the top left with the picture that's in the bottom left, the difference is the standard deviation of the population these samples were drawn from. In the bottom left, I drew samples of 5 people repeatedly from a distribution where the average standard deviation was 5 instead of 3. So the average person is off from the sample mean by 5. And that has an effect on the standard error here, the distribution of these things, to spread them out. So the more variability there is between people in the same sample, the more variability in what the sample mean is going to be across samples. So more variance within a sample translates into a greater standard error of the mean across samples. But more people in a sample makes it better. So if I move from left to right within each of these rows, the distribution shrinks. It gets tighter around the mean that it's supposed to be for the population. So that standard error is going to be smaller in samples that are larger. So if you have more people, you can get a better estimate of what the mean's supposed to be. More people makes it better. So less variance within a sample coupled with more people in the sample makes your results more consistent across samples, where standard error is an index of inconsistency because more is worse. So people versus samples. That's the idea here. I think that was, did we get any further than that? I got a little bit further than that. Okay. I have my chat window open just in case. Any questions so far? No, we're good? Good-ish, maybe? Good adjacent? Good enough? So the technical definition of how we're supposed to find the standard error of the mean is that we use the population standard deviation. Do we have that normally? No. Otherwise, why would we do research yet? I'll make the X buzzer sound. No, we don't. So we can substitute. We can use the sample standard deviation that we actually could get because we have a sample of people for what the population one is, but it might be wrong. At the very least, it's going to be noisier. It's going to be subject to sampling variability, just like the mean. What the standard deviation is supposed to be is going to vary from sample to sample. It's not going to be the right number. So that turns out to have an impact on how good these standard errors are. So just to show you that this works, I computed across these histograms what the standard deviation is of these sample means. That's what the standard error is supposed to give us. And damn if it's not close. So this is where the math works. If you use the population version, it's a little bit closer than if you use the sample version. But even though we only have one sample, that one sample allows us to approximate how noisy the sample mean would be across repeated samples. It's magic. We don't always have magic. Sometimes you have to find the standard error by other means, but in this case we do. So we did this, I remember, showing you that this property, that we can use a normal-ish kind of distribution to characterize the differences across samples and what the mean would be. That's called the sampling distribution of the mean. We can do that no matter what the individual variable looks like. So this is a count variable. It was created using what's called a Poisson distribution, in which the mean and the variance are the same number. So I created this one with the mean of 2 and a variance of 2. And the same tendency happens. It's a little noisier, but the more people that you get, the closer to something that looks like a normal distribution that's peaked in the middle and symmetric on both sides, the mean across the samples is going to be. So we can use this property to try to place what we got for our one sample relative to what we would expect to find to try and make a decision as to whether or not what we got is just a fluctuation that's expected kind of noise, or whether it's discrepant enough to make us question whether or not it's really from that population. Standard error is the magic that allows us to do that. All right, so I think we started talking about confidence intervals. Yes, I remember because I was unsure what unconfident should be called. Anti-confident. So to be able to make some sort of boundary around what we got, that's what the purpose of the confidence interval is. I don't love these, but I have to teach them to you. There's a more intuitive way of thinking about it that we'll do in a bit. But we're going to use for now a normal distribution to characterize how we would expect the sample mean to differ across samples, standardizing the normal distribution so that it is on a common scale where 0 is the mean and the standard deviation is 1. So this is Z is sort of the metric that goes along with that. That would be what you would call the x-axis here. And so these cutoffs in the green, the blue, and the purple refer to values on the x-axis for z within which we can predict what percentage of observations is going to fall if the data that we're talking about, the mean across samples, is characterized by this distribution. So that's where these numbers come from. Their job is to tell us how expected what we found is relative to these cutoffs. If it's outside the cutoff, then it's not expected. It's sufficiently weird, unexpected. So we looked at this for this one sample. If I have a sample mean of 10.98, it's supposed to have come from a population where the mean is 10. Is that weird, or is that within normal fluctuation? Well, if I compute the standard error of the mean using my sample standard deviation, so 4.6 is the standard deviation. A person from this sample is going to be off from the sample mean by 4.6 on average. This sample relative to all the samples in the population, the standard error of the mean here, the 0.65, that tells us that any one sample's mean is expected to be off on average by 0.65 from the population mean. So that number kind of defines what expected fluctuation is, given our sample size and given our standard deviation. And so the intervals that we could form, that would give us 90 whatever percent of the samples would hold the population mean. That's the definition of these things. That's not usually something that is of direct interest, but you will see confidence intervals used to help convey how the strength of the signal of your results. So if you have a result, it's a very different conclusion if you have a tiny window around it than if you have a huge window around it in terms of what it could possibly be across samples. Okay, this I think is where we left off with for real this time, slide 42, talking about hypothesis tests. All right, I'm going to reload and ask if you have questions before we dive in.
Lisa, I have a quick question about the last slide. Just, I think it's my own understanding of it. So the standard error of the mean, like the 0.65, given that it's supposed to be like close to 10, is the 0.65 what we're looking at when we go down then to the confidence interval? Like those should be within 0.65 of okay, right there.
Yeah, so 0.65 is what is used to define the width of the interval, and then the probability that you want to go with it is the numbers that show up right here.
Okay.
And so if you want to be able to say, like, what is the range around 10 that we would expect 90% of our sample means to fall? Like, that's the idea.
Okay, got it.
And so we need the standard error to define the size of the range, because if we had a sample of 1,000 people, the range is much tighter. And likewise, if we had a smaller standard deviation, the range gets tighter.
Okay, got it. Okay, thank you.
Thank you. Okay. So building on that idea then, welcome to your first hypothesis test. Ta-da! You don't look as excited as I would have thought. You can fake it though, right? You can fake it for me? Yeah! Oh, thank you. That is nice and over the top. I appreciate that. So we are talking about trying to make an up or down decision as to whether our results are weird, unexpected. That's what we're trying to determine. And what we can do to provide evidence for whether or not we think it's within normal fluctuation or weird is to compute what is known as, more generally, a test statistic. The job of a test statistic is to place our results onto a standardized metric that we can immediately look at and know what's what. Because otherwise, I'd have to tell you, well, the mean's supposed to be 10 and the standard deviation's supposed to be 5. You'd have to know those things to interpret these numbers. The job of Z and its cousin T that we'll meet later on is to standardize that so that we can say, relative to any mean, how far off are we? So it does that by taking y bar, vocabulary quiz, what's y bar that I'm pointing at here?
Is it the sample mean?
Yeah, sample mean minus u looking thing, which is the Greek letter,
Population mean?
yeah, mu, the population mean. So the numerator of this thing here is how far off are you from what you're supposed to be? So if your mean is higher than you would think, it's a positive number. If your sample mean is lower than it's supposed to be, it's a negative number. Then we standardize based on how discrepant we expect things to be using the standard error. And so this turns into a metric where you're asking how many standard errors off are you from where you're supposed to be? That's what Z tells you. How many standard errors away are you from where you would expect? And so if we plug in the values from this one little example, we're supposed to have a population mean of 10. The sample of 50 people that I pulled had a mean of 10.98, and it had a standard error of 0.65. I've put that into my formula, and I get a Z of 1.5. So then, all right, what the hell does that mean? It means that we are 1.5 standard errors above the mean we're supposed to be. Now, is that too weird? We have to make a decision. And we make a decision about that using standards we've set up a priori, meaning ahead of time so we can't cheat. But if I try to place what we just found onto a standard normal distribution, so this is my, as it's called, a Z curve, where the mean for what we're supposed to get is a 0, and the standard deviation of 1 is a standard error. So we're supposed to get a mean of 10. Our Z value is right here at 1.5. So according to the distribution, if our distribution of sample means from this population follows this distribution, we can predict that we would see a mean that is this high 6.68% of the time, and the rest of the time we would get something that's lower than that. So we would only see a mean that is this discrepant from the population mean about 7% of the time. That's sort of our index of weird. So it's possible, it's not that likely, right? 7% isn't a strong percent, but it's not nothing. So we are at 1.5 standard errors above the mean. That's where we are. And the role of hypothesis tests is to make some sort of arbitrary cut point ahead of time for what too far off is. And this is where it relates to the idea of unconfidence or alpha level, as it is known. So we have to operationalize what is too far away from expected to be believed. So we need a sampling distribution to do that. We'll stick with the normal for now. We need to declare what is too far away in terms of a percentage. So that is known as alpha level. Most commonly in the social sciences, we set our alpha level to 5%, meaning if we get a result that would be expected less than 5% of the time, that's too weird. If you want to be extra lenient, like you want to have a bigger net to catch weird things with because the consequences of weird is too big, you might pick an alpha of 0.10. So anything that happens more than, or that should happen less than 10% of the time is our cutoff. If you want to be conservative, if you don't want to have any false alarms for declaring that something is unexpected, you pick an alpha of 1%. And then if it happens less than 1% of the time, that's my cutoff. So this is something that as a researcher, you would decide ahead of time based on how conservative you want to be and also how many of these tests that you're doing. The more tests that you're doing, the more stringent this cutoff should be so that you don't accidentally think you're finding something that you haven't. That's known as type 1 error, and we'll talk about that in the next unit. And then last but not least, you have to decide whether or not you're willing to be wrong in either direction. So this is what's known as a one-tailed test versus a two-tailed test. And that idea of a tail, let me go back for a second, is the idea of this side over here on the right versus this side over here on the left. Do you count either of them or both of them? So in my view, and I don't think I'm alone in this, two-tailed tests are the way to go because you want to know if your result is too small relative to what you expected or too big. When we talk about finding relationships between variables, like a correlation for whether two things are associated, relative to no association, I'd want to know if I found something where they were negatively related, like as one went up, the other went down, or something where they were positively related, where if one goes up, the other goes up. To me, both of those things are meaningful. And anytime you're in a situation where either side would be meaningful, a two-tailed test is appropriate. So I'm going to issue the edict that one-tailed tests are bullshit voodoo, and we're not going to do them. That's a technical term, bullshit voodoo. There are very, very few situations in which you wouldn't want to know what could have happened on the other side. The only one that I can think of is if you're testing whether or not there is variability. So in samples in which you have more than one kind of sampling, sometimes that is a question as to whether or not there are differences between units at all. So for instance, if I sampled multiple students from multiple different classrooms, one of my questions might be, is the average difference between students, does that depend on which classroom they're in? So I might want to test a hypothesis about variance. In that case, what is the smallest possible number that you think variance could be? The smallest possible value for variance. This is a gesture question or a word question. Yeah, goose egg, 0. What would it mean if a variable had 0 variance? What would we call the variable with no variance?
It's the same or they're equivalent.
Everybody's equivalent. There's a special name for that. It's a constant. If everybody got the same score, that's a constant. So that's the smallest number that a variance could be, is my point, is 0. So in that case, if I were to think about, like, relative to 0, which way variance could go, it can only go up. It can only be a positive number because variance is squared. So there is no other side. So in that case, a one-tailed hypothesis for a variance makes sense because it can't go below 0. But there are very few situations like that where a one-tailed test would make sense. So 2 tails all the way. Another real-world example I can use to describe this is playing pool. You know, back when we used to be able to go places, did any of you like go to a bar and play pool occasionally? Or to a friend's house or something? You know, like hitting balls with a stick, not like swimming, but the billiards. Is that the word for it? Billiards? Billiards. Billiards, okay. So I am not a great pool player, and therefore to me, if a ball goes in the hole, I win, right? Even if it wasn't the ball I was aiming at or the hole I was aiming at. Whereas my husband believes in calling your shot. And if you accidentally hit a ball into the wrong hole, it doesn't count. So you can think of one-tailed tests as the rule that you have to call your shot. You have to have it happen in the expected direction. Whereas two-tailed test is you get the ball in the hole, you win, which is my version. So yes, two-tailed tests all the way. So I have some new vocabulary to map onto this sort of up-down vote as to whether what we've found is sufficiently unexpected for us to think that it's not likely it came from this population. The language that goes along with this is null hypothesis significance testing, where a hypothesis is a word that just means a statement about some population parameter. So we're talking about the mean in this case. The null hypothesis is what you expect. So in our example, because I sampled these data from a distribution that had a mean of 10, that's my null hypothesis. So if I pull any one sample out of this population, it should have a mean of approximately 10. That's what I know to be true. An alternative hypothesis is then what else could happen. And so the idea of a one-tailed versus two-tailed test is saying whether or not our alternative is that the mean is either greater than 10 or less than 10, but one of the other, that's one tail, versus just not 10. And so when you see results from SAS or Stata, you'll see this type of terminology used. Not equal to is either written as an equal sign with a slash through it or the exclamation point. So we're going to do the latter here, the two-tailed test idea. So I'm trying to illustrate here what this would look like to have either a one-tailed test versus a two-tailed test. So let's say that we have 10 as our expected null hypothesis, and we decide on a one-tailed test that the mean is greater than 10. Our result was about, in this case, or hang on, not our result. The boundaries for that decision are shown in the green here. So the cutoff for what above 10 is, where it's far enough above to where it's unexpected, 5% of the area would happen if we hit a z of 1.65, and 95% is the other way. So we would conclude that either our sample mean is bigger than expected or not bigger. So if we ended up with the sample mean that was 9, our conclusion would be that it's not bigger. The pink is the opposite direction. If we did a one-tailed test that it was supposed to be less than 10, then our cutoff is minus 1.65 because that's where 5% would happen. And so if we had a mean that was actually larger than 10, we would say it's not smaller. Now, where this might matter in real life, think about, say, randomized control trials that are trying out drugs to see if they help people. Like, I don't know, vaccines might be a topic of current relevance, right? We're all hoping to get a vaccine so that we can leave our house and play pool someday again. It's a big difference to say, yeah, our vaccine didn't help people if they made them worse, right? The conclusion from a one-tailed test, if you put the tail in the positive that our vaccine should work and it actually makes people worse, the conclusion would be that it didn't help because the whole other side of the distribution is lumped together. So anytime that you have a result that could potentially go either way, two-tailed test. So what does either way look like then? Well, if we want to keep the same total area for what unexpected is of 5%. So if something happens less than 5% of the time, we declare that sufficiently unexpected that it seems unlikely it would come from this population. If we want to be able to say that we have allowed unexpected in the positive direction or the negative direction, we split the area. So we got 2.5% over here on the left side tail and 2.5% on the right side. And the z value that corresponds to that is 1.96 on the positive side or negative 1.96 on this side. So basically, any result that is more than about 2 standard errors away is weird. The exact value is going to depend on your sample size because this distribution turns out to only work well in large enough samples. But 2-ish is a rule of thumb that you can take with you. Any result that is like 2 standard errors away from where it's supposed to be is into the cutoff of 5%. So if we put our example onto this diagram, remember we had a sample mean pulled from this population of 10.98 and a standard error of 0.65. I can make a confidence interval around that for a 95% confidence interval that it will include this. I can do a one sample z-test against a null hypothesis, that's HO right here, of 10, and that gives me my z-value of 1.5 that we had a few minutes ago. So the conclusion then is that we would get a z-value as extreme. So that phrasing as extreme allows for the possibility of a positive z or a negative z because we're not calling our shot ahead of time. So about 13% of the time, we would get a z more extreme in the negative direction, meaning the sample mean is way lower than it's supposed to be, or 6.7% in the positive direction, which is where we are in this case, that it's higher than it's supposed to be. So then if we look at our boundaries, the blue lines define where unexpected starts. So is our result a z of 1.5? Is that expected according to this definition or unexpected? What does thumbs up mean? I need the key for this.
Expected.
It's unexpected. It's within expected territory. Yes. Quite, I mean literally, like we're making a boundary here. So even though it's a little off of where it's supposed to be, it's within expected fluctuation, where expected fluctuation is about 2 standard errors on either side of the mean. So if we think about what goes into standard error, if this sample came from 1,000 people, the standard error would be much smaller. And that means where unexpected starts is closer to 10. If we had a sample of 1,000 people, I bet we would be in the unexpected range because the whole thing shrinks. So the z is standardized so that one unit here is one standard error. So all we have to know is a z of 1.5 and we know which way to go. We don't have to retain the information about what the expected population mean, what we got, what our standard error was. All of that information is standardized into this beautiful z thing. Okay, Jen, did you have a question?
Yeah, could you explain where this p equals 13% is coming from?
Like, where did I get that number or what it means?
Both, but first, where did the number, how did you get that number?
Math. So there's 2 ways, actually, I'll give you 3 ways you can do this. If you had an introductory statistics textbook, inside the back flap will be z tables. And they tell you for any z-score what the corresponding probability is. That's how I learned to do it in college. I got this from the internet. If you ask the Google for, z to p conversion or something like that, you will find a web page where you can type in your z value and it'll spit back the probability. What we will do in practice is that your software will give you the p-value that goes with your z. It has all of that information built into it. So I don't mean to be flip, but it is a distribution that someone has already worked out what the expected probabilities are for any level, any value along this distribution. And so that information just has to be programmed into the routines. Okay, does that answer your question? Okay. So yeah, the p-value in this case is 0.13 because we're using both sides. So a result More extreme than this would happen 13% of the time. About 6 and some change percent of the time, it would be higher than expected, and the other 6, it would be lower. All right, how are we doing? Hanging in there? All right, let me see here. Words? Okay, yeah, words are next. So any other questions before we get to words? Yes.
So the software, does it do like two-tailed tests by default, or can we just program it to do one-tailed as well?
You can ask for whatever you want. In this context, testing a sample mean against a population mean, Stata, for instance, spits out all 3 possibilities, one tail on either side or the 2-tail. I think in SAS, I'm trying to remember, either you can ask for it or it spits them all out and you can pick one. I think most of the time, though, when we get to testing relationships between variables, it spits out 2-tailed as a default.
Two-tailed, yeah.
Yeah, because say it with me, one-tailed tests are bullshit voodoo in the software.
One-tailed tests are bullshit voodoo.
Correct. Okay. Other questions? Okay, words. I did not make these words up. Scout's honor. But I have to have you see them. So I'm going to give you the words that go with these ideas from the classic null hypothesis perspective, and then I'm going to tell you how you would actually talk about it in a paper, because it's not the first way. So this sort of up or down decision that we're talking about, if the test statistic, so in this case all we have so far is a z, the test statistic tells us how many standard errors away from where we're supposed to be our sample mean happen to fall. If that exceeds the distribution's critical value, meaning you're outside the boundaries that you've set, so you're outside the 1.96 that defines 5% in this context, then the p-value, so the term p-value refers to the probability of observing what you found if the null hypothesis is true. So the 13%, for instance, in our previous example, that's the p-value. So if you're into unexpected territory, your p-value is less than your chosen alpha. Alpha is the percentage you decided ahead of time as to where unexpected starts. So in our picture here, this picture is predicated on an alpha of 5%, meaning 2.5 over here, 2.5 over here. If we had chosen a different alpha, then the boundaries of where unexpected starts would either move in if it were a higher alpha, because then there'd be more room for unexpected, or they'd move out if it were a lower alpha, because then it would be harder to cross that boundary and call it unexpected. It'd be, say, only 1% of the time instead of 5. So alpha is your decision a priori of where the boundaries lie that you're, in theory, supposed to make before you even collect data. So if you're into unexpected territory, you reject the null hypothesis. You would say that it is sufficiently unexpected to get a result as extreme as what we got if the null hypothesis is true. Not to say that it can't happen, but it's unlikely, sufficiently unlikely as to be weird. So we would say that the result of this test that we've done, the z-test in this case, is that it is statistically significant. The term significant means unexpected. Would happen less than 5% of the time if that's your alpha level. Now the opposite. If you're in expected territory, if your result is within 2 standard errors on either side, it's not that weird. Then you do not reject the null hypothesis. And someone may fight me about this. I think you can say retain instead. To me, those are appropriate synonyms. Fayaz is laughing because he's like, yeah, I know people who would yell at you about that, right? I think you can say retain. That's my opinion. What you cannot say, though, What you will get yelled at by everyone is if you say you accept the null hypothesis, right? Am I right? Yeah, those of you who've had stats before, that's like the one thing you cannot say that because you don't have evidence to say that. You just don't have enough evidence to reject it. So retain and do not reject are synonyms, and retain to me is easier to wrap my mouth around. So we would say that this result, in which we're within expected fluctuation, is statistically non-significant. And this is another one, you cannot say insignificant. It's non-significant, even though they sound the same. Insignificant would be interpreted as a value judgment. Like, that don't matter. That's so insignificant in the grand scheme of things. Versus non-significant is a term that means the test result was within the expected range. It would happen with greater than 5% probability. So in practice, you will never see in a results section in a real paper the words, "We did not reject the null hypothesis." No one will write like that. They will say, "The result was non-significant, indicating," then whatever that means. In our context, we would say, and I think I wrote this out. Yeah, I did. We would say that our test statistic of 1.5 for a Z means that our result is that we were 1.5 standard errors above the mean we're supposed to be within expected territory, which corresponds to a p-value of about 13%. So 13% of the time we would find what we found, which is greater than 5%. So we would say the test is non-significant, that our sample mean of 10.98 is non-significantly greater than the population mean of 10. So it's two words that go in here, greater or lesser, to convey the direction of what happened, and then significant versus non-significant to indicate the strength of the direction. So significantly greater would be if we're over here on the right, past the blue marker. Non-significantly greater is anywhere from the middle, the null hypothesis, out to the blue barrier. Non-significantly lower would be from the middle out to the blue barrier on the left side, and significantly lesser would be past the blue barrier on the left. So there's sort of 4 quadrants that we're talking about here. And I think it's important to give the direction and the whether or not it crossed the threshold. Because in small samples, you're going to have a harder time saying something is significant. And people who are compiling your results with other similar results will want to know which direction it was headed. So the idea of meta-analysis, have you heard of this before? Yeah, meta-analysis is when you pool the results across studies to try and find like some kind of average result. They'll want to know which way it went, even if it wasn't significant in terms of crossing your threshold. All right. What am I doing next? I got to remind myself what's coming next. Oh, okay. I know what's coming next. Questions? Are we doing okay so far? Okay enough? Okay. So I wanted to show you how well this process works or doesn't work in my simulated data. And here's a spoiler alert. It doesn't work really well in the smaller samples. So the next thing that we get to do is show you a fix to that. So the standard error of the mean is our new best friend. Even though we only have one sample's worth of data, if we know that sample's standard deviation, how different the people are within the sample, the average distance of any person from the mean, and we know the size of the sample, that gives us the ingredients to get a standard error. We can then build a test statistic that tells us how many standard errors away our sample mean is from what the population mean is supposed to be. And we can make an up or down decision as to whether it's too far away, in which case we reject the null hypothesis, we'd say it is significant, or if it's within expected territory, in which case we do not reject / retain, or just say it's non-significant. So this process requires us to know three things. Where unexpected begins, which is alpha. So that's something that you set as a researcher, 5% is the convention. The direction, whether you're going to use a two-tailed test or bullshit voodoo. And then finally the PDF, the probability distribution function, which describes the function by which we can anticipate with what probability we would find a given result. So that shape that we're using to decide where the boundaries are, that thing is the standard normal distribution specifically. There are others. So in our simulated data, so just to remind you, I played God, made 100,000 fake people, and that distribution of 100,000 fake people had a population mean of 10 and a population standard deviation of 5. I then drew 1,000 samples of each of these different sizes, 5, 10, 15, 20, 30, 50, and took the sample mean out of each one and made this picture. So the samples with fewer people have more inconsistency in what their sample mean could be. That translates into a higher standard error. If I were to form a confidence interval for each of these means, then what should happen is that if I pick, say, an alpha of 5%, that translates into 95% confidence. That 95% of the samples should contain my population mean. That's what should happen. However, that didn't exactly happen. We get close to 95% with 50 people, but say if I only have 5, and well, I only have 88% of the samples holding the sample mean. So I didn't get the right result from what's supposed to happen. Said the same thing a different way, this is the same set of plots, but now what I'm looking at is the percent of the time where I reject the null hypothesis, the percent of the time where I say that I got something that was sufficiently unexpected. I'm supposed to be able to say that 5% of the time because that's the definition of what alpha means in this context. I know that these samples all came from the right population, so only 5% of them should be flagged as unexpected. But in the smallest one, it's up to almost 12%. So what happened? This process doesn't quite work in really small samples, but fortunately, people have figured out how to fix it. So the key to noting how to fix it is to note what happens to these standard deviations. So what I'm plotting here on this graph, the x-axis is z. The standard normal distribution is supposed to characterize each of these sampling distributions, and z has a standard deviation of 1. But in the smaller samples, the standard deviation is way higher than it's supposed to be. And so that's part of the reason why I'm getting too many false positives. Too many samples are being flagged as unexpected, is because there's more out here in the tails than what they're supposed to be. So the blue line that's going over the top of these is if this were a proper standard normal distribution with a standard deviation of 1, and you can see that there's some extra samples out here, that's what's messing this up. It's dragging the standard deviation a little bit high. So one way that I could try to fix this is rather than using the sample standard deviation to do this hypothesis test, I could use the population because I have it in this case. Well, that worked. Now I only have 4 to 5% being flagged as unexpected like I'm supposed to. But do you think that I could use that strategy in practice and actually have it work? Could I take the population standard deviation and plug that in instead? Do we have a population standard deviation most of the time?
Yeah, I was gonna say no, but I was nervous to explain why, so no.
Because the population isn't real, right? It's a concept. And I have one because I made up fake people. But if you're collecting data or working with research data that's been collected, you have a sample. If you knew what the population answer was, why would you do the research, right? You already know what you're going to get. So yeah, this strategy of we'll just use the population version is no. But what we can do instead is appreciate the use of beer to the rescue. No, true story. Beer to the rescue. Now, if this were my true story, it would be wine to the rescue, but this is not a story about me. Instead, someone already figured out what we should do in the 1800s. So there was a worker in the Guinness Brewery factory whose name was William Gossett. And he was in charge of quality control. He was supposed to screen various batches of hops for some level of acceptability. So he's measuring. I don't drink beer. I know some people make beer. Do you know what a good thing for hops is? Hoppiness? I don't know what he was going for, but he was in charge of hoppiness quality control of some kind. And so in his process, he had batches that took a long time to grow. So they had very small sample sizes. And he would flag batches that averaged in hoppiness too far away from what it was supposed to be to make Guinness beer. And then those samples that he flagged would get subject to more scrutiny, more testing that was more labor intensive. And what was happening is that too many of the batches that he flagged as potentially being too far out, too far unexpected, were actually fine. And so he's like, what the hell? So instead of just, saying, okay, well, not my problem, he went to graduate school and got a degree in statistics. Guinness let him do this. And he figured out a new distribution by hand, by shuffling cards and drawing samples. Like what I did to play God with my computer, he did that with cards in the 1800s. And he derived this new distribution that's known as the T distribution. And at the time, Guinness would not let him publish because they were worried about trade secrets getting out. And so they made a compromise that he could publish under a pseudonym, which was named Student, and Student's Tea was born. So we have a better process for doing hypothesis tests in small samples thanks to beer. Isn't that a fun story? It's a true story from what I understand. At least I got it from a textbook, so that makes it truer than Wikipedia, perhaps. Although I'm sure you can look this up on Wikipedia. So what's the difference? So this is our friend Z. This is standard normal. That is supposed to describe the probability of observing any one result relative to a null hypothesis of what's expected given standard errors. So that's what this x-axis here, which is called Z, is telling us, how many standard errors away we are. T is a distribution that has a similar shape, but it's flatter. And how flat it is determined by the sample size. So for instance, if we look at these shapes right here, the black line is actually the standard normal Z. If we only have, say, degrees of freedom of 6, by the way, is related to sample size. We can just call it that for now. If we have 6 people in our study, the sampling distribution of the means for when you have samples of 6 looks more like the blue line. If you only have 3, it looks like the red. So the idea of where unexpected should start has to take into account how few people you have. And it gets flatter and flatter the fewer people you have. It makes it harder and harder to say where unexpected starts. So I made a picture here to show you the difference in where unexpected starts as a function of sample size. So the numbers on this t-critical axis here on slide 57 1.96 is the cutoff where unexpected is for standard normal. The same alpha level would result in a cutoff of 2.45 for T if you have degrees of freedom 6, or a cutoff of 3.1 for 3. So it gets harder and harder to cross that unexpected threshold, the fewer people you have in your sample. So here is a picture of what the critical value would be on the y-axis here as a function of what's called degrees of freedom, which is your sample size minus 1. And purple is for an alpha of 0.01, so saying that your result would happen less than 1% of the time. Light blue is for our 0.5, less than 5% of the time, and green is for 0.1, so 10% of the time. And so it takes a lot of people to get to the point where Z is close enough. So Z is given by these dotted lines here. Z don't care how many people you have. It doesn't change. It's 1.96 is your cutoff, the end. T cares how many people you have. And so if you have very small samples, it's harder to get to unexpected territory in T, but that's more accurate because T is naturally flatter. So in our example, if we swap out T instead of Z, so the idea is exactly the same. The difference is in what we call the test statistic and therefore how we define what unexpected is. So we still have the same example data, a sample mean of 10.98 relative to an expected population mean of 10, our null hypothesis, our standard error of 0.65. We have the sample mean minus the population mean divided by standard error. That thing that we used to call a Z is now called a T. And so now we're saying we're 1.5 standard errors away from the population mean. Now let's use a different distribution for where that should be cut off. If we have 50 people, the critical value is 2.01 instead of 1.96. So in this case, it doesn't change what would have happened. Our p-value changes a tiny bit because we have 50 people, and it's not a big difference between T and Z. But in practice, what we're going to use is T. So when you see results comparing a sample mean to a population mean, results asking whether or not there's a relationship between variables, it's almost always going to be T. Because if you have enough people, T turns into Z and it's fine. And so sure enough, if I use a T distribution to get my probability values instead of Z, I get the right amount of alpha without having to know what the population is. And so it's been fixed. Huzzah. All right. Where are we at here? Almost done. How are we doing? So have you seen some of this before or not so much? A little bit? Fayaz, have you seen this stuff before? Yeah. Is it sounding familiar or is it sounding different?
Yes, I have worked with them before, but nobody ever told me the story. That was such a great, like, very interesting.
Students T. Yeah, so the good news though, from your perspective as what we would call a user, but I hate that name, I'm going to go with analyst. Somebody who, because you're not like a drug user or something, like you don't talk about using SAS in the same way that you talk about meth. An analyst does not have to know like this. Let me go back here. Like this picture for what the critical value is. People have figured this shit out. Like you don't have to know this. This is not something that you need to worry about. Because what's going to happen when you ask the software to do these tests for you is that you will get the estimate of whatever you're asking for, like the mean here, its standard error, its t-value, and then it will give you the p-value. And it knows what the right distribution should have been based on your sample size, degrees of freedom, and it knows what the probability is going to be. Like this is easy territory in terms of math that people know that works like it's supposed to. It's not always the case like that, but in this case it is. So I just wanted you to get a sense of like why you see different letters sometimes. Z is acceptable if you have enough people. But in practice, we use T just in case you don't. So you'll get results phrased in T's for pretty much the rest of the semester.
Yeah, so I have worked with R before,
Mhm.
and the outputs I get, I used to treat them as Z scores, but now I know and I have seen in the outputs, I just like, didn't care about them, but they are actually T distributions because the samples were really small, like less than 500.
So R is like the wild, wild west. Like each person makes their own package, and I don't know necessarily what a given package is going to do the way that I know like what a SAS package does because they have, documentation and programmers. But here's how you can tell. If you get as part of your results a column that says something like degrees of freedom or denominator degrees of freedom, it's T.
Okay.
That's how you know, because Z doesn't have that. So both T and Z are distributions that are appropriate when you're testing one thing. So in this case, one sample mean. The T versus Z is just the flatness. And if you have enough people, they converge onto basically the same distribution. I was always taught that enough was like 30. That was sort of something that stuck in my head. But looking at this chart, that's not really true. It depends on your alpha level, where these things start to converge and you can say that it's good enough. So I'd say maybe like 100 people or something is where the differences wouldn't matter that much. But yeah, if you see degrees of freedom, it's a T. If you don't, it's a Z. The analog to testing multiple things, by the way, is exactly the same. If you're testing multiple things without degrees of freedom, that's a chi-square. Z squared is chi-square. That's coming next unit. If you test multiple things with degrees of freedom, so paying attention to how flat the thing should be, that's F, and T squared is F. So every test result that you get is going to be one of those four letters, T, Z, chi-square, or F. And I don't know why people decided on those letters, but those are universal. Like, that is what people say.
So can I ask one final question?
Please.
So if somebody in the audience asks me, like if I'm presenting this, they ask me what kind of distribution you are using for this analysis, and if I say that I'm using Z distribution, which was actually T, then I would be wrong, right?
You would be wrong technically speaking, but it may not make any difference. No one will ever ask you that. That is never going to happen. Maybe like in a comps defense or something to where like they're trying to like, test you, but no, that is not a thing. What they might do instead though is question why you selected a particular analysis method, and then you might have to defend that. But the use of T versus Z, like no one's gonna ask you about that in a talk. Reviewer 3 might. I'll take that back. Reviewer 3 might. So nowadays it's Reviewer 2, though. I'm part of a Facebook group called Reviewer 2 Must Die or something like that. It's people complain about the review process. I think that's what it's called. It's something to that effect. Yeah, you can ask the Facebook about it, but it's a whole collection of people complaining about Reviewer 2. So, anywho, all right. Yeah, degrees of freedom. Okay, last thought, and then we'll adjourn for the day here since we're at a summary point. So you will hear this phrase, degrees of freedom. So there's two kinds. There's numerator and there's denominator. Numerator refers to how many things you're testing at once. So right now we're just testing one mean. Denominator refers to how many people you're doing it with. And so denominator degrees of freedom starts with sample size, and then you take one off for every term that you had to estimate in order to do what you're going to do. So you can think of degrees of freedom as like money or like points. So I put an article on your reading list this semester that I got. It's Joe Rogers has a sort of a tutorial / approach to talking about degrees of freedom as statistical money that I really like. The way I think of it is like Weight Watchers points. So like it used to be the case where you could like say, based on your size and your weight loss goals, you can eat like 30 points worth of food in a day. And broccoli is 1 point and pizza is 10 points. And it's like when you've eaten all your points, you put your fork down. And so it's up to you to decide how to allocate the points. By the way, there was a thing in the 1980s called Deal a Meal that was hosted by Richard Simmons that was the exact same thing. It was like a wallet full of cards. But it's the same idea. Like in our formulas that we've seen so far for the mean or for the variance, when we first calculate the mean, the denominator, which is why it's called denominator degrees of freedom, is n. But in order to get the variance, we already had to know the mean. So then we lost a point. If we had to know something else, it'd be n minus 2. And so t is phrased in terms of this denominator for how many points we have left. That's what denominator degrees of freedom means. So if I have a denominator degrees of freedom of 6, that means that I could have had 7 people and spent 1 point, for instance. All right. Yeah. Slide 61. We're making progress. By the way, you know enough to already do the first half of your first assignment. I haven't made it available yet because I'm waiting to make sure that everything goes okay with homework 0. But these are the kinds of things that you'll be asked to do, is just to find means and descriptive statistics. And then the second half gives you practice testing them, just like this. All right. Any other questions before we call it a day? No? All right. Then enjoy some Guinness beer, celebrate statistics. Have a good weekend and let me know if you need anything. Bye for now.
Hey, Lisa, sorry, I do have a quick question. I was just
Sure.
glancing at the syllabus. I think the syllabus on our class website still has that homework 6 is due on the 21st, but maybe that's...
You might have to clear your cache or reload it. The one that I have it pulled up has it correct, unless it's you mean the paper document?
Okay, yeah, let me try
Let me make sure
again
that
here.
one got updated too.
So just refresh the page.
Yeah, sometimes you have to actually like clear the memory for the page for the new version to come up. I've found that before with Chrome especially.
Okay.
Let me make sure that the paper version is, the paper version is updated because I have a last updated footer on here so that I can keep track. So.
Okay. I will try to clear it then because I think mine keeps pulling up the old one. So.
Okay.
Okay, great.
But yes, if I screw up any more dates, please let me know, folks.
Okay. All right. Thank you.
Sure. Anything else? Let's go. Okay. All right then. See you next week. Stay safe. Thanks for coming.